5th October 2021. Scientific background on the Nobel Prize in Physics 2021. For groundbreaking contributions to our understanding of complex physical systems. The Nobel Committee for Physics. Introduction. This year's Nobel Prize in Physics focuses upon the complexity of physical systems, from the largest scales experienced by humans, such as Earth's climate, down to the microscopic structure and dynamics of mysterious and yet commonplace materials, such as glass. We recognize that scientists understand that no single prediction of anything can be taken as unassailable truth, and that without understanding the origins of variability, we cannot understand the behavior of any system. Only then, for example, do we understand that global warming is real and attributable to humans. In the following, we begin with a general background to provide a context for the discussion of specific contributions. A central emphasis is on the physical reality that the variability in the basic processes, from climate dynamics to frustrated materials, leads to the emergence of multiple length and timescales, and hence is fundamental to interpretation of theory, experiment, and observation. Instability and nonlinearity underlie multiscale complexity and stochasticity. The emergence of disorder from order, and with it multiple scales in space and time, is a characteristic of complex systems. Understanding the nature of that disorder presents an enormous scientific challenge. Natural questions include: does it grow in space and time without bound? Does it choose a particular spatial structure or many spatial structures? Does that choice involve all of the degrees of freedom of a system or just a subset? Which subset? The questions themselves have the same multi-scale structure as the phenomena they address. A quintessential example is the transition of a laminar flow to a turbulent flow, e.g., 866-104. But in this and other nonlinear systems, characterizing the border between order and disorder is amongst the most challenging problems in physics. Indeed, advances in understanding multiscale physics have been prominent in turbulence theory and experiment, e.g., 10, 36, 64, 67, 88, and the linkages between statistical physics and hydrodynamic instability underlie the generality of the problem, 92. Turbulent thermal convection, such as what happens when we boil water, is an ideal setting for demonstrating the role of a myriad of scales in controlling macroscopic transport of heat and mass, 23, 51. This was on the mind of Edward Lorenz when he built his toy model of convection in the atmosphere, 56, which is a Galerkin modal truncation of the equations for Rayleigh-Benard upper and lower boundaries, 97. The model is dx dt equals sigma times y minus x, dy dt equals x times ra minus z minus y, and dz dt equals xy minus beta z, where x describes the intensity of convective motion, d is the temperature difference between ascending and descending flow, and z is the deviation from linearity of the vertical temperature profile. The control parameters are the Prandtl number, sigma, which is a property of the fluid, the Rayleigh number, Ra, which is the dimensionless buoyancy driving vertical fluid motions, and a constant factor beta, characterizing the domain geometry. The Lorentz system acts as a rich toy model of low-dimensional chaos. Since its origin, the breadth and extension of studies has been so broad, e.g., 103, it would be difficult to enumerate them all. Key here are the fact that the solutions are bounded, Fig 1, and yet exhibit sensitive dependence on initial conditions, Fig 2. 20. Y. 0. Minus 20. 0. X. 10. 20. Minus 30, minus 20, 30, z, minus 10, 0, 10, 20, 30, 40, 50, 60, 70, 60, 80, 90, 100. Fig 1. Plot an x, y, z phase space of numerical simulation of a circuit version of Lorentz system at sigma beta Ra equals 10, 8/3, 33.5 from Wadey et al. 2018. Poincaré is generally credited with launching the field by discovering that the long-term behavior of the three-body problem was infinitely more complex than had been anticipated.
In modern parlance, he observed the tangling of homoclinic orbits, which are trajectories of a dynamical system flow, joining a saddle equilibrium point to itself, residing at the intersection of the stable manifold and the unstable manifold of an equilibrium, and inferred the divergence of the perturbative solutions to the equations of motion. He recognized that the Sol system could be viewed dynamically as a perturbation of the integrable Kepler-Hamiltonian problem. The complementary pictures of statistical mechanics and hydrodynamics continue to inspire and challenge researchers. From the perspective of the phase space of 5, 10, 15, 20, t, -15, -10, -5, 5, 10, 15, x. Ig2. Plot of xt of the Lorentz system with sigma, beta, Ra equals 10, 8/3, 24.9, in which the initial data for all three variables, read 10 or 10.01, read. The divergence of the two solutions with slightly different initial conditions begins at t equals 5.5. This is sensitive dependence on initial conditions, often whimsically referred to as the butterfly effect. Evolution of the probability density of a system may be accessible via the Boltzmann, Fokker-Planck, or Liouville equations, 27. Such high-dimensional partial differential equations may be intransigent to useful analysis. In contrast, lower-dimensional ordinary differential equations may exhibit shockingly complex chaotic dynamics, e.g., 5, 56, 103. However, either formally, 105, or in specific physical systems, such as those governing atmospheric dynamics, 57, the effective dynamics may operate on lower-dimensional slow manifold. In consequence, it is reasonable to ask whether climate, the signal, is the low manifold of weather, the noise. Of course, such a question is at the heart of the work being honored this year, and is being asked across a vast range of disequilibrium systems, where one replaces climate and weather. In other systems, a central aspect of such questions is how one distinguishes between internal, external, and emergent phenomena. B. Stochasticity and disorder imply predictability. The relation between the signal and the noise in classical Brownian motion assumes equipartition and hence thermal equilibrium. However, in systems out of equilibrium, the situation can be dramatically different. Giorgio Parisi, 87, highlights the distinction between equilibrium and non-equilibrium systems as follows. But the situation is different for systems that are only slightly out of equilibrium. For example, imagine a system that cannot reach equilibrium because of high free energy bars that may be of energetic or of entropic nature. This situation typically applies to disordered systems, such as spin glasses and structural glasses. Such a system will ap one metastable state to another, and it could remain slightly out of equilibrium forever if continually perturbed with a slowly changing external field. In such systems, we can expect a separation by many orders of magnitude between the microscopic timescale of the system, for example, that represented by the vibrations of individual atoms, and the macroscopic time needed to cross the barrier, for example, changes in the structure of the system itself. The system can then be considered to be essentially thermalized inside a metastable state, and so fluctuation dissipation ideas can still be applied. The slowly changing overall state of the system is considered to be a small perturbation. This basic manner of thinking, be it for spin glasses or any other complex stochastic multiscale system, such as climate, characterize much of the landscape of the work being recognized this year. Indeed, it is essential to understand that noise and disorder influences all systems and can entirely determine the fate of some nonlinear dynamical systems. Thus, the concept of predictability is spacious when one ignores the underlying causes of noise-induced variability. I. Climate physics, background and history. Since Fourier's studies of the Earth's energy budget, shortwave solar radiation has been known as the central input of energy into the climate system. The spectral separation between this input, centered in the visible, and the output in the infrared, underlies the nature of the habitability of any planet with an atmosphere that absorbs in the infrared. The heating effect of the absorption of solar radiation by CO2 and other gases was measured, but in 1861, John Tyndall, 1.0, published a then technological tour de force of systematic absorption and emission of infrared radiation by a wide variety of gases, including water vapor and CO2.
The experimental foundation for future study of what we now call the greenhouse effect, and was a key ingredient in the major advance made in 1896, Svante Arrhenius, 6, Nobel laureate 1903, whose work we discuss more below. The absorption and emission of infrared radiation by Earth's atmosphere is, apart from any other physics operative in physical climatology, physically and computationally challenging area of broad relevance in planetary physics. 9.1. The history of physical climate science is described through major waypoints in the published literature collected by Archer and Pierhumbert. 4. Indeed, the ease with which we can now all run online radiative transfer models, which we show next, might leave the likes of Tyndall shocked. Figure 3 shows the results of the moderate resolution simulates the emission and absorption of infrared radiation in the Earth's atmosphere. When CO2 is added to the atmosphere, the infrared radiation escaping to space is reduced in the spectral range shown in the middle panel. A big bite appears at a wave number of about 50 centimeters minus 1, which is responsible for the reduction in outgoing radiative flux from the planet. Water vapor dominates the spectral range up to about 500 centimeters minus 1, and then again at large wave number. The smaller bite centered at about 1050 centimeters minus 1 is due to ozone. In order to re-establish a steady-state energy balance, the wings surrounding it, which are dominated by water vapor, must radiate at a higher temperature. In this example, the surface temperature increases by 8.5 degrees. Water vapor dominates the spectral range up to about 500 centimeters minus 1, and then again at large wave number. The smaller bite centered at about 1050 centimeters minus 1 is due to ozone. Spectra such as seen in Figure 3 inform our understanding that the most potent greenhouse gas, GHG, in Earth's atmosphere is water vapor, whose distribution we cannot directly control. It is simply not possible to control when, where, and how much rain falls. Rather, atmospheric water vapor is controlled by the complex hydrological cycle, and basic thermodynamics demonstrates that for every degree increase in temperature, the atmosphere can hold approximately 7% more water. This is the basis of the so-called water vapor feedback. As the planet warms, the amount of water vapor in the atmosphere, thereby increasing the temperature, and so forth. Understanding how that water vapor is distributed through the action of the hydrologic cycle is a major challenge. In principle, we can control the Earth's temperature by controlling other GHG concentrations. The simple question to ask is, given an increase in atmospheric CO2, what are the consequences for global physical climatology? Like most clear questions in the physical sciences, the path towards an answer is a punctuated process, informed by both mistakes and successes. The Keeling curve in Fig 4 shows the key observations during our lifetimes. The curve is iconic both because of its analytical precision and its foreboding message. During the last 8 glacial cycles, about 800,000 years, the CO2 concentration has not been higher than 300 ppm, with a maximum glacial interglacial change of about 120 ppm and temperature anomalies greater than 10 K. How does one model such a system that contains so many cogs and wheels? 3. Development of model hierarchies. A. Energy balance models. The input of solar energy acts as the largest annual external periodic thermal forcing to the climate system. Figure 3. The vertical axis is the total upward infrared energy flux in Wm squared, and the horizontal axis is wave number, Cm-1. The smooth curves are theoretical emission spectra black bodies at different temperatures. The jagged lines are spectra of infrared light at the top of the atmosphere looking down on Earth. The model demonstrates the effect of wave wavelength-selective greenhouse gases on Earth's outgoing energy flux. Here, we take an extreme version of increasing atmospheric CO2 from 0 ppm to 1000 ppm in the top panel. In the top panel, there is no CO2 in the atmosphere, and the outgoing steady-state flux is 249 Wm-2. In the middle panel, 1000 ppm CO2 is distributed through the atmosphere, and the absorption bite, highlighted by the downward-pointing black arrow, reduces the instantaneous flux escaping from the top of the atmosphere to 223 Wm-2. In the lowest panel, in order to re-establish steady state with 249 Wm-2, the wings surrounding it, dominated by water vapor and highlighted with the upward black arrows, must radiate at a higher temperature, in consequence of which the surface temperature increases by 8.5 degrees C. Online models are available at http://climatemodels.uchicago.edu.
CO2 concentration, ppm. Carbon dioxide concentration at Mauna Loa Observatory. September 10, 2021. Full record ending September 11, 2021. 1960, 1965, 1970, 1975, 1980, 1985, 1990, 1995, 2000, 2005, 2010, 2015, 2020, 310, 320, 330, 340, 350, 360, 370, 380, 390, 400, 410, 420. IG4, the Keeling curve, named after the late Charles E. Keeling, who began the monitoring program. The curve shows monthly mean CO2 concentration from Mauna Loa, 1958-2021. Data from Scripps Institution of Oceanography. https://keelingcurve.ucsd.edu. Practice of climate must rely on the challenging edifice of explicitly time-dependent differential equations to capture the time evolution of climate subsystems on many timescales. On the other hand, numerical modeling, which marches forward the coupled equations of the entire system in the modality of weather forecasting, can incorporate time-dependent forcing in a variety of ways. It is self-evident that the atmosphere, ocean, cryosphere, and masses and biosphere must obey the laws of thermodynamics. However, the myriad of timescales in the globally coupled system make determination of which subsystems are in what balance on a given timescale challenging theoretical exercise. The canonical class of energy balance models, now referred to as Buddy-Coe-Sellers models 15, 28, 78, 101, balances the incoming shortwave and outgoing longwave radiation fluxes against each other. In a mean annual, globally averaged sense, we can write Cp dt over dt equals S0, 1 minus alpha minus E sigma T4. Here, T is the temperature of the surface, Cp is its effective heat capacity, S0 and alpha are the solar shortwave, radiative flux, and surface albedo respectively, sigma is the Stefan-Boltzmann constant, and E the emissivity. The fixed point for this simple model is E sigma T4 BP equals S0 1 minus alpha. Can continue Ti up equals Fo up equals Fi down, feeding U shown. Figure 4. The Keeling curve, named after the late, for that the incoming solar flux, Fo down, is balanced by the upward surface flux, Fo up, which gives us the steady-state temperature, Tbp, equals 4p S0 1 minus alpha over E sigma. The atmosphere only enters into this result through the use of the planetary albedo alpha, which is approximately 0.3 as determined from satellites, thereby including both highly reflective clouds up to 0.9 and absorbing oceans 0.2. Hence, TBP does not include the infrared contribution due to the greenhouse effect.
In consequence, this is often referred to as a bare planet temperature, and it is core, TBP, approximately minus 15 C, 591. Now, the simplest means to see the infrared effect of the atmosphere is shown in Figure 5. In steady, I up atmosphere, I down atmosphere, I up ground, boundary to space, FA, FA, FG. FI, Fig. 5, approximately as envisioned by Svante Arrhenius, 1896, a one-layer atmosphere over Earth that absorbs and emits the outgoing infrared radiation from the surface, FG up. We assume the outgoing atmospheric emission is the same as the incoming and that the atmosphere is isothermal, so that FA down equals FA up equals FA. Modified from 5. State balance, balancing the fluxes in the atmospheric layer, have Fg equals 2FA. And, using this at the surface, we find FO down equals FA at the top of the atmosphere. The two key consequences are A. The top of the atmosphere radiating to space at the cold, bare planet temperature, Ta equals Tbp, and B. The surface temperature is now a balance equation, Tg equals 2 to the 1/4 Tbp. Generalizing this to an n-layer atmosphere, one find that Tg equals 1 plus n to the 1/4 Tbp, with the top of the atmosphere radiating to space at Tbp, with the clear implication of a runaway greenhouse effect that ignores the subtleties of the spectral absorption of greenhouse gases, feedback, and many other effects. These leading order processes were understood by the polymath Svante Arrhenius, 1896, a in a pioneering study of how carbon dioxide absorption would influence Tg. He built the scientific framework central to the atmospheric column models used in successively more complex treatments that have developed since then. The effect now known as band saturation was also understood by Arrhenius, who was using the then available state-of-the-art spectroscopic data on CO2 and water vapor, and, in particular, that from the experiments of Tyndall, 109. In band saturation, the absorption increases linearly with temperature at low gas concentrations or pressures, but with increasing concentration, infrared radiation entering a gas is absorbed, not on rated. Present spectroscopic measurements also show that CO2 is far from being saturated, 91. Moreover, we now understand that because of the vertical structure of both the gas concentration and the temperature, even where the atmosphere saturated, Tg can still rise because the radiation escapes to space from the thin, diffuse upper layers that are not saturated. Finally, Knut Ångström argued that increasing CO2 would have little radiative impact because water vapor absorbs the infrared radiation that CO2 would absorb were its concentration to increase. Whereas this effect is operative in the lower, very high humidity tropical atmosphere, CO2 influences the part of the infrared spectrum associated with the cold upper layers of the atmosphere radiating to space. In consequence, Ångström's argument was superfluous, 491. Arrhenius's prediction, now referred to as climate sensitivity, was to estimate the change in Tg upon a doubling of the atmospheric CO2. Modern estimates have the range of 2.5 to 4 degrees C, and Arrhenius predicted approximately 6 degrees C, which was limited by the accuracy of the absorption spectra and his treatment of the atmosphere roughly as shown in Figure 5. With the advent of modern spectra, this latter approximation underestimates the climate sensitivity, because the effect described in the previous paragraph, wherein CO2 influences the range of the infrared spectrum associated with the cold upper layers of the atmosphere radiating to space, cannot be incorporated. This underestimate was offset by the spectra he used. Arrhenius also highlighted other key components of modern physical climatology. In particular, the equator-to-pole energy imbalance and the ice albedo feedback. The latter effect, wherein a latitudinally dependent albedo in EQ1 underlies the two basic states of the climate system, cold and warm, is of central contemporary popular and technical interest with the rapidly evolving ice pack in the Arctic. Indeed, he made excellent predictions of the CO2 concentration during an ice age of 150 ppm, which we know from ice core research, 25, was 180 to 200 ppm, as well as making estimates of how human coal consumption would lead to a doubling of atmospheric CO2. All of this was done in a single paper, in which he provided the conceptual scaffolding of contemporary atmospheric column models used in various incarnations today. In that sense, the central influences of anthropogenic greenhouse gas forcing on climate have been understood for a century, and Arrhenius's work is truly prescient as a sheer intellectual tour de force, laying out the basic ingredients for analysis in the present day. See the discussion in 4. B. Generalized Deterministic Energy Balance Models, EBMs. As introduced above in Section 3A, the simplest models explore the radiative transfer properties of the atmosphere. These are generalized to mean annual zonally averaged, that is, across latitudinal bands, whilst allowing for a latitudinal dependence of Tg and alpha and meridional longitudinal heat transport. Such a framework admits a time-evolving planetary ice line and hence a spatial ice albedo feedback. If a perturbation slightly expands the ice cover, less energy is absorbed by the system, it cools further, EQ1, the ice expands further, driving the cooling feedback. Indeed, such theories predict an abrupt transition to a completely ice-covered or snowball Earth when the solar flux S0 is lowered by just a few %. Of such approach can be solved analytically, 79, to find 3 fixed points. The snowball and the interglacial, present states, are both stable states, whereas that with approximately 2/3 ice cover is unstable. The approach within this class of theories can be solved using spectral methods akin to those used in numerical simulations of the Navier-Stokes equations, 77. Although clear observational evidence of ice ages had long been known, too, the multiple global climate stats predicted by a range of EBMs were results that we viewed as unrealistic theoretical predictions. However, contemporaneous interest in nuclear winter, where weapon-suspended dust blocks incident solar radiation, constituted another interest in their predictions. Only the last few decades has evidence been found for a global glaciation about 700 million years ago, 54-100, in the Neo-Proterozoic, highlighting the role of EBMs 15-10 as quantitative tools. Importantly, such theories capture the possible multiple states of the climate system and contain mathematically interesting and generalizable features that connect them to a broad class of multi-state systems appearing across many problems in physics, as described in Section 3. In this sense, climate science stimulates research in other areas of physics. C. The emergence of numerical climate model. 1. Prelude. All models are approximations to reality. All approximations, be they mathematical or the numerical implementation of formula, break down in particular limits. The art and science is to make rational approximation. The rigor is associated with knowing with high precision the circumstances of the breakdown. Since the ready availability of large-scale computation, the term model in climate science nearly uniformly appears to be synonymous with global climate models, GCMs, rather than EBMs. Contemporaneous GCMs operate in the same manner as did the original incarnations, by numerically solving the conservation of mass, momentum, and energy throughout the atmosphere, ocean, ice system with parameterizations representing subgrid scale. Improved GCMs use data assimilation, 94, and test and implement high-resolution schemes, 52. Due to the complex nature of climate, particularly fluid, systems, GCMs are amongst the most sophisticated numerical models developed. Nonetheless, despite the enormous progress made in the development of GCMs, completely resolving the spatio-temporal processes in the climate system remains a challenge, particularly in the high latitudes, 1. Furthermore, because of the complex structure and high-dimensional data produced by GCMs, it is not straightforward to extract the dominant physical processes on multiple timescales with the aim of interpreting their mutual interactions. Thus, GCMs operate like enormous coarse-grained weather forecasts. The global climate is represented by the output from a computational approximation of all of the known physics and, most importantly, parameterization of subgrid scale processes and, often ad hoc closure schemes connect different subsystems. Recent advances in climate models systematically embrace the concepts spearheaded by Klaus Hasselmann, 42, that the chaotic dynamics in the weather underlie the variability on longer timescales and ultimately must be treated in models, e.g., 11, 20, 29, 59, 80, 81. 2. Origins. The difference between the incoming solar energy and the outgoing infrared energy is a function of latitude with substantial excess of 5 pW between 40N and 40S. That energy is transported to the high latitudes by the motion of the atmosphere and the ocean, and hence the quantitative fate and distribution of that heat focuses attention on the basic mechanisms of fluid flow and mixing in a rotating system. The atmosphere carries about 2/3 of the 5 pW, and the remainder is transported by the ocean, but on different timescales and constrained by geography. Thus, the reality of theories and models is constrained by the treatment of these issues, as well as the cryosphere due to the ice albedo feedback. During the 1950s, large-scale numerical weather forecasting originated at the Institute for Advanced Study in Princeton in a project led by Jules Charny and John von Neumann, 19. This naturally evolved roughly in parallel with the theoretical and experimental study of the detailed processes of atmospheric and oceanic dynamics, generally referred to as geophysical fluid dynamics, GFD 14-115. Although over time, a cultural difference between GFD, weather forecasting, and climate modeling has led to different communities, they clearly share many similar goals, if not approaches. Many pioneers were recruited and/or visited for long stays, and these people, including Bert Bolin, brought international expertise to the project. 112. Key here is the involvement of Joseph Smugoritsky, head of the U.S. Weather Bureau's General Circulation Research Laboratory, which later moved to Princeton to become the Tsukuro Manabe in 1959 and Kirk Bryan in 1961. The laboratory soon had a large staff of programmers. Working independently, by 1960, Cecil E. Leith developed, coded, and was running what could be considered the first comprehensive atmosphere-only GCM, AGCM, as the history is described in detail in a recent article. 3. The model had a domain up into the lower stratosphere and a representation of the hydrological cycle and clouds. Leith produced animations of the runs and hence all stood at the forefront of computer visualization. 3. Key results. The numerical models being recognized, 61 to 63, were built upon solid physics and can be considered as the first realizations of the dream of Arrhenius. Important early studies, 60-75, focused attention on how to incorporate known dynamic and radiational processes into a column model, 62. Manabe and Weatherald, 62, treated the entire atmosphere as a single one-dimensional column with a given profile of relative humidity and greenhouse gas concentration. It evolves from an initial state, A, via radiation transfer, which is calculated given the spectra of greenhouse gases, the most important being water vapor, A, by convective adjustment. This process constitutes parameterization of the vertical dynamics as follows. A column evolves solely from radiative transfer. The lap rate is circa minus 15 degrees C per kilometer, far greater than observed. Note the adiabatic lapse rate is circa minus 10 degrees C per kilometer, but as air rises in a real atmosphere, the condensation of water releases latent heat, which is largely responsible for the observed or moist lapse rate of circa minus 6 degrees C per kilometer. To model this phenomena, whereby surface heating drives vertical movement, phase change, and the consequent release of heat, soon as the temperature profile deviates from the moist lapse rate, it is adjusted back to it. This is the convective adjustment scheme of Manabe and Strickler, 61. Manabe and Weatherold, 62, noted that observations show rather little seasonal variation in the climatological latitudinal relative humidity profiles in the northern hemisphere, whereas the absolute humidity, saturation vapor pressure, will depend sensitively on temperature. Thus, Manabe and Weatherold, 62, repeat the calculation of Manabe and Strickler, 61, with the key difference between the two being that the earlier paper used to given distribution of relative absolute humidity, which appropriately captures the water vapor feedback discussed above. As described in the arguments surrounding Figure 5, the upper layer of the atmosphere radiates to space at a low temperature, and to get the energy balance there quantitatively correct, the relative humidity, embodying the most important greenhouse gas, the concentration of other greenhouse gases, and the temperature must be captured. This confluence of effects led to the key result of Manabe and Weatherold, 62, which are doubling of atmospheric CO2. By 1975, Manabe and Weatherold, 63, had substantially advanced their 1967 column treatment by solving the Euler equations for heat, mass, momentum, and radiation around the globe, their first GCM, using a computer with about 0.5 megabytes of RAM. When they doubled Ca2 from 300 to 600 ppm, the globally averaged surface temperature increased by 2.93 degrees C. The model assumes no transport of heat by the ocean, idealized topography, and a fixed distribution of clouds amongst others. As described in Section 3A, Arrhenius introduced the concept of climate sensitivity, which is still used today. However, one needs to distinguish the difference between the Arrhenius concept, or the equilibrium climate sensitivity, ECS, from the transient climate sensitivity. In TCS, one envisions an instantaneous doubling of CO2 and then calculates the new steady-state energy balance with little veracity ascribed to the time it takes to reach that steady state. An extreme version of increasing atmospheric CO2 from 0 ppm to 1000 ppm is shown in Figure 3, in which the moderate resolution atmospheric transmission (MODTRAN) model is used to demonstrate the idea of the ECS. MODTRAN simulates the emission and absorption of infrared radiation in the atmosphere in the same manner as Manabe and Weatherold, 62, but with modern spectral data and methods. When CO2 is added to the atmosphere, the infrared radiation escaping to space is reduced in the spectral range shown in the middle panel. But in order to re-establish a steady state, the wings surrounding it, dominated by water vapor, must radiate at a higher temperature, in consequence of which the surface temperature increases by 8.5 C. This calculation rebalances the column energy in the same general sense as did Manabe and Weatherold, 62-63, and asks for the new surface temperature that achieves this. Contemporary GCMs produce a climate sensitivity range of 2.5 to 4 degrees C, and the two rather different Manabe and Weatherold models produce a range 2.3 to 2.93 degrees C. As described in Section 3A, we know why the Arrhenius result for ECS of approximately 6 degrees C is an upper bound. Accounting for accuracy of absorption spectra and an isothermal atmosphere, but the robustness of the Manabe and Weatherold results is remarkable, suggesting further that increasing model complexity may not increase fidelity of prediction. In reality, the greenhouse gas profile is evolving over time, and hence so too is the response of the climate, which is what underlies TCS. Thus, humanity is really influenced by transient climate sensitivity. Both CS and TCS are model-dependent, and it was Klaus Hasselmann who suggested a scheme for systematically assessing how models compare to evolving observations. D. Stochastic theories. Planetary climate reflects a myriad of interactions operating over a wide range of space and timescale. The spatially inhomogeneous distribution of shortwave radiative flux drives the atmosphere and ocean fluids dynamically, leading to long-ranged communication through fluid advection and wave propagation, e.g. 32. Whilst the GCMs described above attempt to capture these processes, computing a sufficient number of realizations to quantify variability is a perennial challenge. Therefore, a great deal of interest in how to quantify variability in a true statistical central limit theorem sense emerged in both observational and theoretical studies. At the same time that the deterministic models of Manabe and his many collaborators were focusing on building GCMs. To provide context, consider a global Budicco-Seletic ECM, such as shown in equation 1, and assume that the actual surface temperature T is not far from the average surface temperature Ts, such that T equals Ts plus X, with X much less than Ts, e.g. 73. The high-frequency fluctuation, such as those associated with weather, are represented as white noise, eta, with constant amplitude, xi, so the time evolution of X is represented by what is called overdamped Ornstein-Uhlenbeck process, or generalized Langevin equation, dx dt equals minus lambda x plus xi eta, with lambda equals 4 xi t over SS0 minus xi alpha over dt, Cp, where lambda represents the overall deterministic stability, the climate relative to the equilibrium temperature Ts. The albedo sensitivity, d alpha over dt, is negative, there exhibiting positive feedback, whereas the sensitivity of the outgoing long-wave radiative flux is positive, there stabilizing deviations from Ts. Analysis of observations of the spectral properties pressure fields, 76, in the context of signal processing motivated Mitchell, 71, to posit an autonomous Langevin equation description of the ocean climate. At the same time, Klaus Hasselmann was creatively using fundamental physics concepts to quantify the surface ocean wave spectra, 40-41, thereby building a deep appreciation for the nature of fluctuations on the sea surface. Building on the intuition garnered from this research, basic concepts in turbulence and Lorenz's chaotic weather, see section IA, he derived a generalizable stochastic description of ocean climate, in which the noise is associated with the weather, as described above. 42. His work has provided both the motivation and the observational structure. Outline of the Hasselmann 42 stochastic framework. Here we provide an interpretive and notationally unuttered outline of the Hasselmann approach. Consider the climate system of interest to be described by a coupled set of governing equations represented by the vectors x equals x1 ... xi and y equals y1 ... yj, captured by two sets of functions fi and ga as .xi equals fi of xy and .yj equals ga of xy, 5, in which the characteristic timescales of evolution of all the xi are much shorter than those of all of the y, where the latter treat the evolution of a slowly evolving, large-scale climate observables. With no loss of generality, we further simplify the situation and treat x and y as scalar variables, allowing us to write the effective dynamics for y in terms of the fast variable as x equals bracket x under bar y plus x star, where bracket x under bar y is the conditional average, the average of x conditioned on the state of y. Because x varies more rapidly than y, we use the conditional dynamics in that for y as g of bracket x under bar y plus x star y approximately g of bracket x under bar y plus dxg of bracket x under bar y x star equals negative du of y dy plus bar s of y g of t. Here we have assumed that the rapid variations in the fast variable x star of t can be approximated as white noise with bracket x star of t prime equals delta of t minus t prime, an amplitude that depends on the state of the slow variable s of y and the deterministic dynamics that is interpreted as a drift force of the potential u of y. Finally, when the intensity of the noise is small, the system will spend a long period of time near a fixed point, say ye, around which the drift force can be expanded and the noise amplitude is ostensibly constant. Then the dynamics of the climate variable y of t is reduced to an Ornstein-Uhlenbeck process of the form of equa 3, i.e. dy dt equals negative lambda y plus bar s g of t. This treatment in terms of Brownian motion concepts allows for the study of climate variables in the framework of stochastic differential equations. For example, in addition to studying the state of the system via equa-6, one can study the probability of the system being in a given state at a given time, because to every Langevin equation there exists a Fokker-Planck equation, e.g. 22. This is a framework particularly useful in interpretation of climatological observations. Moreover, the solution to equa-6 gives the autocorrelation function r of tau equals bracket y of t plus tau, the Fourier transform of which is the power spectrum. P of omega equals bar s of omega squared over omega squared plus lambda squared, showing A, the red noise response of the white noise process in equa-6, and B, the most basic form of the spectrum to that of the variance of the process, viz. W bracket y squared equals bar s of lambda. It is important to emphasize that, unlike Mitchell, Hasselmann did not invoke equa-6 directly as an observationally motivated ansatz. Rather, he begins with equations 1, which are better suited as a framework for stochastic parameterizations in climate models, e.g. 11, 20, 29, 59, 81. Importantly, there are of course an enormous range of timescales in the dynamical system that is climate, and the existence of clear separations are at the heart of modern understanding of climate variability, e.g. 29. Central to Hasselmann's approach is the deterministic averaging described above, giving a coupled slow-fast deterministic system controlled by a multiplicative noise correction to the averaged forcing. As described by Cully et al. 20, this aspect has only recently been rigorously justified, but under more restrictive conditions than proposed by Hasselmann. As shown in Figure 6, while the spectrum grows as the frequency decreases, we expect eventual saturation because of the finite dissipation, lambda. However, it has been shown by Hasselmann, Wunsch, e.g. C113 and Refstheer, and others that the ocean has an impressively long memory of events that can be hundreds to thousands of years old. Moreover, on the decadal timescales of relevance to humans, evidence is consistent with the memory being effectively infinite. Hence, this suggests a potent self-similarity or fractal character, in which multiple timescales provide different classes, e.g. brown, white, red-pink, of stochastic processes, 72. Therefore, the base observation that a data record can be non-stationary has a growing variance and a difficult-to-measure mean amongst the basic tenets of climate variability emerging from Hasselmann's work on the analogy with Brownian motion, Fig. 6. The first application of the Hasselmann stochastic model, 42, for climate variability to climate data, 26. The spectrum of the sea surface temperature, SST, in the period 1949 to 1964 in the North Atlantic. The 95% confidence interval is given by the double-headed arrow, and lambda 1 equals 4.5 month. Clearly, this approach can and has been generalized and taken into many directions in this and many other fields. However, the theoretical framework in which O might fruitfully treat climate data, and hence climate spatio-temporal fingerprints, such the time-varying three-dimensional changes in GHG concentrations, provide a means of discrimination between observed changes and natural variability. Through 3 years of refinement, 45 through 49, the procedure is far more rigorous, nuanced, and comprehensive than is comparison of model simulations with observations alone. One begins with a filtered version of the observed record, given by the vector y, and the regression takes standard form, y equals xa plus u, where the matrix X contains the estimated response patterns to the external forcing or signals that are of interest. A is a vector of scaling factors that adjusts the amplitudes of those patterns, and U represents internal climate variability, typically assumed to be a Gaussian random vector with covariance matrix C. The vector A is estimated in terms of C and Y with a variety of statistical techniques, where signals estimated with one or another mode, either a GCM or EBM, to create internal variability with a complex spatial temporal structure. For an observed response to be attributed to anthropogenic forcing, X must contain separate natural and anthropogenic responses, and hence A must account for possible error in forcing amplitude tuned to match the model to the observations. In this manner, detection and attribution are determined through a combination of physical reasoning and evaluation of specific hypotheses concerning the scaling factors within A. Importantly, the results rely on estimation of the exact fingerprint amplitudes from observations and are independent of whether or not the climate models used correctly simulate the fingerprint amplitudes, e.g. 48 through 49. In a recent article celebrating the anniversary 3 key events in climate change science, Santer at decades since the 1979 Charney Report, 19, which was the same year as Hasselmann's first paper on how models and observations can be self-consistently compared. There are 4 sections to the paper, 98, the first being a summary of the Charney Report, and the second tied Hasselmann's optimal detection paper, 43, which the authors refer to as the first serious effort to provide sound statistical framework for identifying a human-caused warming signal. This approach was a departure from previous work in univariate statistics. Instead of looking for a needle in a tiny corner of a large haystack and then proceeding to search the next tiny corner, Hasselmann advocated for a more efficient strategy, searching the entire haystack simultaneously. He also pointed out that theory, observations, and models provide considerable information about signal and noise properties. These unique signal characteristics, or fingerprints, can be used to distinguish climate signals from climate noise. From the Charney Report, which relied on basic theory and early climate model simulations, there was clear recognition that fossil fuel burning would yield an appreciable global warming signal, 19. Klaus Hasselmann's paper, 43, outlined a rational approach for detecting this signal. Satellite-borne microwave sounders began to monitor atmospheric temperature, providing global patterns of multi-decadal climate change and natural internal variability information required for successful application of Hasselmann's signal detection method. Hasselmann's paper was a statistical roadmap for hundreds of subsequent climate change detection and attribution, D&A, and provided strong scientific support for the conclusion reached by the IPCC in 2013. It is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. V. The vastness of the landscape of disorder. A. Replicas, spin glasses, and frustration. The term spin glass was coined in the early 1970s to describe disordered magnetic systems that appeared to have a phase transition to a state in which each magnetic atom was stably aligned, but with the essential proviso that the alignment direction varies randomly between atoms. Imagine a triangle with magnets placed north poles up or down. Under intuitive circumstances, say upon placing the triangle in an external field pointing up or down perpendicular to its plane, one might imagine all 3 either up or down. Now we impose an antiferromagnetic constraint that any adjacent pair must have the opposite orientation. When 2 magnets satisfy the constraint, 2 others do not, and no amount of flipping orientations will satisfy the constraint. The system is frustrated. This extremely idealized setting is one of the simplest means to see how spin glasses and other systems are frustrated. Many frustrated systems are frustrated in their own ways, and there are many from which to choose, including structural or ordinary glasses and marginal Gardner glasses. This is not the forum to discuss the vast range of glassy systems, but a common feature of such systems is that when they are rapidly quenched, they are unable to access equilibrium and persist in occupying a plethora of very long-lived metastable states. When a given experimental system typically has a unique measurement, numerical and/or conceptual protocol. This system specificity has remained a central challenge in the field from its inception, e.g. 1268-96. Philip Anderson, Nobel laureate 1977, argued that the history of spin glass may be the best example I know of the dictum that a real scientific mystery is worth pursuing to the ends of the earth for its own sake, independently of any obvious practical importance or intellectual glamour. B. Solving the replica symmetry breaking problem. For brevity of illustration, we can consider a spin glass as system of impurities or spins with a Hamiltonian. H equals minus x I k j I k sigma I sigma k, where the j I k are uncorrelated Gaussian random variables with 0 mean and variance j squared I k equals k I k. Frustration emerges by allowing both ferromagnetic and antiferromagnetic couplings, and hence we expect corrugated energy landscape with many long-lived metastable states. Within this framework, we can sketch the developments in general heuristic terms. Edward and Anderson considered a short-ranged interaction so that KIK decreases rapidly with I minus K distance. Importantly, they constructed an order parameter for the spin glass phase that is the projection of a spin onto its original orientation, allowing one to neglect long-range spatial ordering and instead consider long-range temporal ordering. Thus, upon waiting for a long period of time, if their order parameter is finite, the spins remember their original orientation and in that sense form a glass. Moreover, in order to average over macroscopic samples wherein a vast number of different configurations of the RIC, making n copies or replicas of the partition function viz. lnz equals lim n approaching 0 zn minus 1 upon n, hereby allowing properly averaged thermodynamic calculations f equals negative kt lnzf. In the same year, Sherrington and Kirkpatrick 102 came up with an infinite dimensional version of the Edson-Anderson model, so that KIK equals n-1, where n denotes the total number of spins. Whilst this allowed for valid mean field calculation, it also revealed a paradox. The entropy became negative at low temperature. Due to the many states with very nearly equal energies and to clear symmetry, computing convergent solutions was a great challenge. The challenge, however, led to the idea of simulated annealing, 53. In quick succession, Thouless, Nobel laureate 2016, Anderson and Palmer, 106, resolved the negative entropy problem but were left with the question of the stability of their solutions, and then the Almeida and Thouless, 21, pointed the finger at the problem that replica symmetry was assumed. This led to calculations of broken replica symmetry by Blandin, 3, and by Bray and Moore, 14, but the subtleties of just how to break replica symmetry were still elusive. Giorgio Carisi solved the problem of replica symmetry by realizing that, in contrast to ferromagnets, which have only two pure states, up-down, in the ordered phase, there must be an infinite number within the ordered phase of the spin glass, 82, 83. Not only did this provide the solution, but it had a stunning array of extensions to a wide range of spin glass in other systems, 68, 69, 84, 86. In order to realize the infinitude of states, Parisi's great app was to introduce a new order parameter. Q alpha beta equals 1 upon n summation I, comma curly bracket sigma I, curly bracket alpha, curly bracket sigma I, curly bracket beta. Herein alpha and beta are replicas. All of the Q alpha alpha are equivalent, representing the average overlaps of the states within a given replica, and the off-diagonal terms measure the degree to which alpha and beta resemble each other. Namely, they describe the average overlap between states belonging to replica solution alpha and those belonging to replica solution beta. In the glassy phase, there is no unique locally stable thermodynamic state, but many states, each replica of which corresponds to a different solution to the mean field equations. These solutions are clusters of states in the n-dimensional configuration space of the n spins. The mathematics are beyond the scope of this venue. A key concept is called ultrametricity, which is a functional version of the triangle inequality, which we all know from early school days. The sum of the lengths of any two sides of a triangle are greater than or equal to the length of the third. Here, ultrametricity can be characterized using a network describing the states of states. At random, at least two overlaps are equal, so that the disorder average distribution of overlaps is P of Q equals summation alpha beta W alpha W beta delta function Q minus Q alpha beta, where the W's are Boltzmann weights. See applications and implications. The broad reach of broken replica symmetry concepts and methods has exploded since Parisi's original work. In particular, Parisi and his collaborators have shown that in John Hopfield's neural network model, 50, and its many offspring, the multiple memories stored in the network correspond to the multiple equilibria of the spin glass. Moreover, their methods allowed them to address the classical optimization problem of the traveling salesman, who stops at many local minima, but of course the global minima are the targets of interest, 66. At the time at which the book was published, David Thowles wrote, 107, "I feel that the spin glass experts are like settlers encamped in hostile territory. They have interesting observations to make, but have not learned how to communicate with the earlier settlers. In some of the papers on neural nets, there is barely a reference to work by scientists outside the spin glass community."
Clearly, in the more than 3 decades since, the Earth settlers have colonized widely across many communities. These include A. Providing a basic understanding why some optimization tasks are easy and why some are very difficult. C. 70 and refs therein. B. The random first-order theory of structural glasses. And C. The geometric theory of jamming in hard spheres, which an extremely successful application of mean-field broken replica symmetry, applying as it does from 2 to infinite dimensions. 89. The approach sets the agenda for experiments in classical granular matter, 9, and is confirmed in detailed numerical analyses, 16, 17, 95, in equilibrium, and under slow compression, 93. Moreover, the marginal phase predicted by the replica theory of glass has been directly observed experimentally in a slow densifying colloidal glass, 37. Importantly, evidence of replica symmetry breaking has been provided in systems using random lasers, 30, 33, 99, 108, plain cavity lasers without disorder, but with frustration between interacting lasing modes without added disorder, 7, 74, and in nonlinear optical propagation through photorefractive disordered waveguides. Finally, the nature of the random laser system allows for the concomitant observation of replica symmetry breaking and connection between spin glasses and turbulence, 34, particularly nonlinear wave interactions, which link the of disorder and fluctuations in complex systems in general. Random lasers and replica symmetry breaking. As noted above, one of the exciting areas in which the two-peaked signature of first-order replica symmetry breaking, predicted by EQ10, is in random lasers, wherein stimulated emission is complicated by the medium in one manner or another, 30, 33, 99, 108. Because the energy density is controlled by the pump power, the latter acts as the inverse temperature. Thus, as the pump power increases, the nonlinearity in the system plays the role of corrugating the energy landscape, analogous to the low-temperature behavior in a glass. On the other hand, for low pump power, the cavity modes are ostensibly independent of each other, which is analogous to the paramagnetic phase of the spin glass. Importantly, random laser has a large number of metastable states, whereas a chaotic laser has a small number of modes that can exhibit exponential path divergence. This leads to different spectral properties for each type of laser. Minima PQ, -1, 0, 1, 0, 100, 200, 300, 400 Q. PPQ, 0.4 mJ, A, 0, 100, 200, 300, 400 PPQ. Q. Minima PQ, -1, 0, 1, 0, 100, 200, 300, 400 PPQ. 6 mJ, E, 0, 100, 200, 300, 400, 500 PPQ. Minima PQ, -1, 0, 1, 0, 100, 200, 300 PPQ. 10 mJ, F, 0, 100, 200, 300 PPQ. Minima PQ, -1, 0, 1, 0, 100, 200, 300, 400 PPQ. PPQ, 3 mJ, D, IG7, the distribution PQ of the overlap Q alpha beta for different pump energies, shown in the inset, from 30. As discussed in the text, the pump energy plays the role of the inverse temperature. As the pump energy increases, the distribution of first-order replica symmetry breaking appears. Gofraniha et al. 30 quantify spectral data from a random laser and analyze the fluctuations in emission between different shots. The idea is that each emission spectrum defines a replica, say alpha, of the random laser under the same conditions. If the intensity fluctuation function is delta alpha of k equals I alpha of k minus I bar of k, where I bar of k equals P alpha I alpha of k by n is the average intensity at each wavelength indexed by k, then the Parisi overlap function EQ9 becomes Q alpha beta equals P alpha k delta alpha of k delta beta of k,
P alpha k squared, P delta beta squared. It is observed that there is a much larger spectral variation at strong pumping, low T, and the variance of the emission intensity changes discontinuously at a particular energy, exhibiting a phase transition, Fig 3:30. After having generated many shots, a direct measurement of PQ is realized and demonstrates first-order replica symmetry breaking as shown in Fig 7. That the same result is found in different random laser systems, 99, speaks to the robust nature of this demonstration of replica symmetry breaking. Whilst we have dwelt upon the realization of replica symmetry through the lens of fluctuation, stochasticity, and disorder, Giorgio Parisi has been involved in uncovering the scaffolding of and developing the tendrils between a stunning range of physical systems. A subset of these includes stochasticity in quantum field theory, the intermittency of turbulence, Euclidean random matrices, non-equilibrium fluctuations in glasses, stochastic interfacial motion, granular matter, and the role of random fluctuations in controlling Earth's climate states over long epochs. Summary. Clearly, this year's laureates have made groundbreaking contributions to our understanding of complex physical systems in their broadest sense, from the microscopic to the global. They show that without a proper accounting of disorder, noise, and variability, determinism is just an illusion. Indeed, the work recognized here reflects, in part, the comment ascribed to Richard Feynman, Nobel laureate 1965, that he believed in the primacy of doubt not as a blemish on our ability to know, but the essence of knowing. 32. Recognizing the work of this troika reflects the importance of understanding that no single prediction of anything can be taken as inviolable truth, and that without soberly probing the origins of variability, we cannot understand the behavior of any system.
Therefore, after having considered these origins, do we understand that global warming is real and attributable to our own activities? That a vast array of the phenomena we observe in nature emerge from an underlying disorder, and that embracing the noise and uncertainty is an essential step on the road towards predictability. 1. Agarwal S., Wetlaufer, J.S., 2018, Fluctuations in Arc D, B, L models. Phil Trance R. Sock, A. 376, 2017 0332. All, D, F, B, L. Changes, Proc Nat Academ Sci USA 97 1331-1334. 3. Anderson P.W., 1988, Spin Glass I, A Scaling Law Rescued, Phys Today 41 526. 4. Archer D. and Pierre Humbert, editors, 2011, The Warming Papers, The Scientific Foundation for the Climate Change Forecast, Wiley-Blackwell, Hoboken, N.J., 432 pages. 5. Archer D., 2006, Global Warming, Understanding the Forecast, Wiley, 208 pages. 6. Arrhenius A., 1896, On the Influence of Carbonic Acid in the Air upon the Temperature of the Ground, Phil, Mag. 41, 237-275. 7. Basak S., Blanco A., Lopez C., 2016, Large Fluctuations at the Lasing Threshold of Solid and Liquid State Dye Lasers, Sci Rep. 6, 32134. 8. Bachelor G.K., 1953, The Theory of Homogeneous Turbulence, Cambridge University Press, 212 pg. 9. Beringer R.P., Chakraborty B., 2019, The Physics of Jamming for Granular Materials, a review, Rep. Prog. Tes. 82, 012601. 10. Benzi R., Paladin G., Parisi G., Volpiani A., 1984, On the Multifractal Nature of Fully Developed Turbulence and Chaotic Systems, J. Phys. A., 17, 352131. 11. Berner, J., and 26 others, 2017, Stochastic Parameterization Toward a New View of Weather and Climate Models, Bull, M. Met, Soc. 98 3, 565-587. 12. Binder, K., Young, A.P., 1986, Spin Glasses, Experimental Facts, Theoretical Concepts, and Open Questions, Rev. Mod. Piz. 58 800. 13. Blandon, A., 19 1978, Theories versus Experiments in the Spin Glass Systems, J. Phys. Collect 39, C6, C6-1499 to C6-1516. 14. Bray, A. Moore, M. 1978, Replica Symmetry Breaking in Spin Glass Theories, Phys. Rev. Let. 41, 1068. 15. Boudico, M. I. 1969, The Effect of Solar Radiation Variations on the Climate of the Earth, Tellus 21, 611-619. 16. Charbonneau, P. Corwin, E. I. Parisi, G. Zampani, F. 2012, Universal Microstructure and Mechanical Stabilization of Jammed Packings, Phys. Rev. Let. 109, 205501. 17. Charbonneau, P. Kirchen, J. Parisi, G. Urbani, P. Zampani, F. 2017, Glass and Jamming Transitions from Exact Results to Finite Dimensional Descriptions, Anu Rev. Condimet, Phys. 8, 265. 18. Charney, J. G. Fjortoft, R. Von Neumann, J. 1950, Numerical Integration of the Barotropic Vorticity Equation, Tellus 24, 237-254. 19. Charney, J. G. Arakawa, A. Baker, D. J. Bolin, B. Dickinson, R. E. Goody, R. M. Leith, C. E. Stommel, H. M. Wunsch, C. I. Carbon Dioxide and Climate, A Scientific Assessment. 20. Kulina, J. Krafthoff, S. and Monahan, H. 2011, Stochastic Parameterization Schemes for Use in Realistic Climate Models, J. Atmosphere 68, 284. 21. De Almeida, J. R. L. Thulis, D. J. 1978, Stability of the Sherrington-Kirkpatrick Solution of a Spin Glass Model, J. Phys. 11, 983. 22. Doering, C. R. 2016, Mathematical Foundations of Stochastic Processes, 2015, Program of Study, Stochastic Processes in Atmospheric and Oceanic Dynamics, J. S. Wetlaffer and O. Buehler, eds., Woods Hole Oceanographic Institution, Tech Rep. WHOI 2016 05 140, Die 1015/1912-8061. 23. Doring, C. R. 2020, Turning Up the Heat in Turbulent Thermal Convection, ProcNet Acadic Sci USA 117 AF 91 to AF 94. 24. S. S. Edwards, F. Anderson, 1975, Theory of Spin Glasses, J. Physics F. Metal Physics 5 965. 25. EPC Community Members, 2004, 8 Glacial Cycles from an Antarctic Ice Core, Nature 429 623-628. 26. Franknikoff, C. Hasselmann, K. 1977, Stochastic Climate Models, Part 2, Application to Sea Surface Temperature Anomalies and Thermal Climb Variability, Tellus 27, 289-305. 27. Gardner, C. Stochastic Methods, Springer, Berlin, Heidelberg, Germany, 4th edition, 2009. 28. Gill, M. 1966, Climate Stability for a Sellers-Taylor Model, J. Atmosphere 33, 3-20. 29. Gill, M. Luciani, V. 2020, The Physics of Climate Variation and Climate Change, Rev. Mod. Piz. 93, 03502. 30. Goffreniha, N. Viola, I. Di Maria, F. Barbarella, G. Gu, Louisi, L. Conti, C. 2015, Experimental Evidence of Replica Symmetry Breaking in Random Lasers, NatCom 6, 6058. See also corrigendum in regards to F4. 31. Glantz, M.H. Katz, R.W. Nichols, N.I. 1991, Teleconnections, Linking Worldwide Climate Anomalies, Volume 535, Cambridge, Cambridge University Press. 535 PG, 32. Glick, J. 1992, Genius, The Life and Science of Richard Feynman, pp. 489, Open Road Integramedia, NY. 33. Gomez, A. Raposo, E. Mora, A. et al., 2016. Observation of Levy distribution and replica symmetry breaking in random lasers from a single set of measurements. S. Rep. 6,
27987. 34. Gonzalez IRR, Raposo EP, Macedo AMCS et al., 2018. Coexistence of turbulence-like and glassy behaviors in a photonic system. Sci-Rep 817046. 35. Guckenheimer J. and Holmes P. Nonlinear oscillations, dynamical systems, and bifurcations of Vec fields. Springer, New York, NY, 1983. 462 pg. 36. Halsey T.C., Jensen M.H., Kadanoff L.P., Procacia, Schreiman B.I., 1986. Fractal measures and their singularities, the characterization of strange sets. Phys. R.A. 33 114115. 37. Hammond A.P., Corwin E.I., 2020. Experimental observation of the marginal glass phase in a colloidal glass proc. Nat Acad Sci. USA 117-5714-5718. 38. Hansen J., Russell D., Rind P., Stone, Lasis A., Levin S., Travis L. 1983. Efficient three-dimensional globe models for climate studies. Models I and II. Mon W. Rev. 111-609-662. 39. Hamilton K. 2020. At the dawn of global climate modeling, the strange case of the Leith atmosphere mod. Hist. Geospace Sci. 11 931-103. 40. Hasselman K. 1966. Feynman diagrams and interaction rules of wave-wave scattering processes. Rev. Geophys 4 132. 41. Hasselman K. 1967. Nonlinear interactions treated the methods of theoretical physics with application to the generation of waves by wind. Proc. R. Soc. A. 297 70-100. 42. Hasselman K. 1976. Stochastic Climate Models, Part Theory. Tellus 28 6 473-485. 43. Hasselman K. 1979. On the signal-to-noise problem in atmospheric response studies. In Meteorology and Tropical Oceans. Ed. by D. B. Shaw. London, Royal Meteoralsoc, pp. 251-259. Detection of Time-Dependent Climate Change. J. Climate, 6, 1957-1971. 45. Hasselman, K. 1997. Multi-pattern fingerprint method for detection and attribution of climate change. Clim. Dyn. 13, 601-611. 46. Hegerl, G. Hasselman, K. Kubosh, U. Mitchell, J.F.B. Rockner, R. Voss, R. Waskevitz, J. 1997. Multi-fingerprint detection and attribution analysis of greenhouse gas plus aerosol, and solar-forced climate change. Clim. Dyn. 13, 613-634. 47. Hegerl, G. North, G.R. 1997. Comparison of statistically optimal approaches to detecting anthropogenic climate change. J. Clim. 10, 1125. 48. Hegerl, G. Zwiers, F. Tabaldi, C. 2011. Patterns of Change. Whose fingerprint is seen in global warming? Environ Res. Let. 6. 044025. 49. Hegerl, G. Zwiers, F. 2011. Use of models in detection and attribution of climate change. Wires, Clim. Change 2, 570-91. 50. Hopfield, J. 1982. Neural networks and physical systems with emergent collective computational properties. Proc. Nat. Academy Sci. USA. 79, 2554-2558. 51. Iyer, K.P. Scheel, J. Schumacher, J. Srinivasan, K.R. 2020. Classical one-third scaling of convection holds up to Ra equals 1015. Proc. Nat. Academy Sci. USA. 117, 7594, 7598. 52. Jung, T. Miller, P. Palmer, T. Towers, P. Weddy, N. Achuthavariye, D. Marks, L. 2012. High-resolution global climate simulations with the ECMW model in Project Athena. Experimental design, model climate, and seasonal forecast skill. J. Climate, 25, 3155, 3172. 53. Kirkpatrick, S. Gilat, C. D. Vecchi, M. P. 1983. Optimization by simulated annealing. Science, 220. 671, 680. 54. Kirschvink, J. L. 1992. Late Proterozoic Low-Latitude Global Glaciation. The Snowball Earth. In the Proterozoic Biosphere. Edited by J. W. Shop and C. Klein, pp. 51-52. Cambridge University Press, New York. 55. Canuti, R. Sedlacek, J. 2013. Robustness of uncertainties in the new CMIP5 climate model projections. Nature Climate Change. 3. 369, 373. 56. Lawrence, E. N. 1963. Deterministic Non-Periodic Flow. J. Atmosphere. Sci. 20, 130-41. 57. Lawrence, E. N. 1992. The Slow Manifold. What is it? J. Atmosphere. Sci. 49, 2449, 2451. 58. Lyubativza. Gvishiani. A. D. Solovyev. O. O. Samohina. Krasnoperot. R. I. 2020. 60th Anniversary of the International Geophysical Year. 1957 through 2017. Contribution of the Soviet Union. Hist Geospace Sci. 11, 1571, 171. 59. Majda, A. Timofeyev, I. and Vanden Einden, E. 2001. A Mathematical Framework for Stochastic Climate Models. Communes Pure Applied Math. 54, 981, 974. 60. Manabe, S. Muller, F. 1961. On the Radiative Equilibrium and Heat Balance of the Atmosphere. Mon Weatherrev. 89, 503-32. 61. Manabe, S. Strickler, R. 1964. Thermal Equilibrium of the Atmosphere with a Convective Adjustment. J. Atmosphere. Sci. 21, 361-85. 62. Manabe, S. Weatherold, R. 1967. Thermal Equilibrium of the Atmosphere with a Given Distribution of Relative Humidity. J. Atmosphere. Sci. 24, 241-259. 63. Manabe, S. Weatherold, R. 1975. The effects of doubling the CO2 concentration on the climate of a general model. J. Atmosphere. Sci. 32, 3-15. Similar cascades. Divergence of high moments and dimension of the carrier. J. Fluid Mechanics. 62, 331-58. 56. Mann, M. E. Steinman, B. A. and Miller, S. 2020. A sinus of internal multi-decadal and interdecadal oscillations in climate model simulations. NatCom 1, 1-9. 57. Malkus, W. V. R. 2001. Borders of Disorder. Stud App, Math. 107, 325, 336. 58. Menaveo, Srinivasan, K. R. 1987. Simple Multifractal Cascade Model for Fully Developed Turbulence. PRV Let. 59, 1424, 1427. 59. Mazard, M. Parisi, G. Veracero, M. 1987. Spin Glass Theory, and Beyond. An Introduction to the Replica Method and its Applications. World Scientific, Singapore. 476 pages. 60. Mazard, M. Parisi, G. Sorlas, S. Toulouse, G. Veracero, M. 1984. Nature of the Spin Glass Phase. PRV Let. 52, 11. 61. Mazard, M. Parisi, P. and Zekchina, R. 2002. An analytic and algorithmic solution of random satisfiability problems. Science 297, 812. 62. Mitchell, J. M. Jr., 1966. Stochastic models of air-sea interaction and climatic fluctuation. Semta Machina, A.
On the AT heat budget and atmospheric circulation. Lake Arrowhead, California, 1966. Mem. RM 5233-NSF. The Rand Corp., Santa Monica. 72. Moon, W. Augerwal, S. Wetlaufer, J.S. 2018. Intrinsic pink noise multi-decadal global climate dynamic. Mode, Phys. Rev. Let. 121-108701. 73. Moon, W. Wetlaufer, J.S. 2019. Coupling functions climate. Bill Trans, R. Soc. A. 377-001006. 74. Mora, A. E. L. 2017. Replica symmetry breaking in the photonic ferromagnetic-like spontaneous mod-locking phase of a multi-mode ND-YAG laser. Phys. Rev. Let. 119-163902. 75. Muller, F. 1963. On the influence of changes in CO2 concentration in air on the radiation balance of the Earth and on the climate. J. Geophysics, Res. 61-3877-86. 76. Monk, W. H. 1960. Smoothing and Persistence. J. Meet, 1792-93. 77. Orzag, S.A. 1971. Galerkin approximations to flow within slabs, spheres, and cylinders. Phys. Rev. Let. 26-1100-11. 78. North, G.R. 1975. Theory of Energy Balance Climate Models. J. Atmosphere, Sci. 32-2033-43. 79. North, G.R. 1975. Analytical solution to a simple climate model with diffusive heat transport. J. Atmosphere, Sci. 11-1300-07. 80. Palmer, T.N. 2000. A nonlinear dynamical perspective model error. A proposal for non-local stochastic dynamic parameterization in weather and climate prediction mods. Q. J. R. Meteorol, Soc. 127-279-304. 81. Palmer, T.N. 2017. The Primacy of Doubt, Evolution, Numerical Weather Prediction from Determinism to Probability. J. Add, Model, Earth, Syst. 92-730-74. 82. Parisi, G. 1979. Toward a Mean Field Theory for Spin Glasses. Phys. Let. A. 73-203. 83. Parisi, G. 1979. Infinite number of order parameters for spin glasses. Phys. Rev. Let. 43-1754. 84. Parisi, G. 1980. Magnetic properties of spin glasses in a new mean field theory. J. Physics, A. Math Gen. 1, 1887. 85. Parisi, G. 1983. Order parameter for spin glasses. Phys. Rev. 43-1754. 86. Parisi, G. 1988. Statistical Field Theory. Addison, Wesley. Redwood C. C.A. pp. 352. 87. Parisi, G. 2005. Brownian Motion. Nature 433-221.
88. Parisi G. Frisch U. 1985. On the singularity structure of fully developed turbulence. In Turbulence and Predictability in Geophysical Fluid Dynamics. Ed. M. Gill, R. Benzi, G. Parisi. pp. 84-87. Amsterdam, North Holland. 89. Parisi G. and Zamponi F. 2010. Mean Field Theory of Hard Sphere Glasses and Jamming. Rev. Mod. Phys. 82, 1, 789. 90. Pierangeli, D. Tavani, A. D. May, et al. 2017. Observation of replica symmetry breaking in disordered nonlinear wave propagation. Nat. Com. 8, 1501. 91. Pierre Humbert R.T. 2011. Principles of Planetary Climate. Cambridge Univ Press. Cambridge, pp. 684. 92. Pomeau, Y. The Long and Winding Road. 2016. Nature, Phys. 12, 198-199. 93. Raynon, C. Urbani, p. 2016. Following the evolution of glassy states under external perturbations, the full replica symmetry breaking solution. J. Stat. Mech. Phi, and X. 053302. 94. Rollins, F. Ballard, SP. Bovis, C. Clayton, A. Lee, Inverarity, G. Payne, 2007. The Met Office Global Four-Dimensional Variational Data Assimilation Scheme. QJ, Royal Meteorolo, SOC, 133-347-362. 95. Risson, P. Corwin, E.I., Parisi, G. 2021. Long-Range Anomalous Decay of the Correlation in Jammed Packings. Phys. Rev. Let. 127-03800. 96. Reed, N. 2014. Short-Range Ising Spin Glasses. The Metastate Interpretation of Replica Symmetry Breaking. Phys. Rev. E. 90-03142. 97. Saltzman, B. 1962. Finite Amplitude Free Convection as an Initial Value Problem. I. J. Atmos Psi. 19, 329-341. 98. Santer, B. D. et al. 2019. Celebrating the anniversary of 3 key events in climate change science. Nature, Climb, Change, 9, 180-182. 99. Sarkar, A. Shivakaran Bhakta, B.N., Andreasen, J. 2020. Replica Symmetry Breaking in a Weakly Scattering Optofluidic Random Laser. Psi. Rep. 10, 2628. 00. Schrag, D. Berner, R. Hoffman, F. Halverson, G. 2002. On the Initiation of a Snowball Earth. Geochem, Geophys, Geosys, 3, 6, doi, 1010219. 01. Sellers, S. 1969. A global climatic model based on the energy balance of the Earth-atmosphere system. J. App. Meteor, 8, 392-400. 02. Sherrington, D. and Kirkpatrick, S. 1975. Solvable Model of a Spin Glass. P. Shaw, Let. 35, 1792. 03. Strogatz, S. H. Nonlinear Dynamics and Chaos. Westview Press, 2000. 512 page. 04. Sweeney-Fassen, R.A., Antonia, R.A., 1997. The Phenomenology of Small-Scale Turbulence. Annual, Rev. Fluid Mech, 29, 435-72. 05. Tamam, R. Infinite Dimensional Dynamical Systems in Mechanics and Physics. Springer, New York, N.Y., 1997. 06. Thallis, D.J., Anderson, P.W., Palmer, R.G., 1977. Solution of Solvable Model of a Spin Glass. Phil, Mag, A. 35, 593. 07. Thallis, D.J., 1988. Phys. Today, 41, 12, 110. 08. Tomasi, F. Ignesti, L. Lepri, S. Cavalieri, S. 2016. Robustness of Replica Symmetry Breaking Phenomenology in Random Laser. Psi. Rep. 6, 37113-09, Tyndall, J. 1861, on the absorption and radiation of heat by gases and vapors, and on the physical connection, Magazine, Series 4, 22, 169-194, 273-285, 110, Untersteiner, N. 2009, International Geophysics Year, 1957, 1958, Drifting Station Alpha documentary film, National Snow and Ice Data Center.org/10.7-2658-9TW, or nsid.org/G2184-111, Wetlaufer, S. 2016, Editorial, Climate Science, A. Invitation for Physicists, Phys. Rev. Let. 115000-112, Wynne Nielsen, A. 1991. The Birth of Numerical Weather Prediction, Tellus, A. 43, 4, 36-52, 113, Wunsch, C. Modern Observational Physical Oceanography, Understanding the Global Ocean, Princeton University Press, Princeton, N.J., 2015, 114. The founders of this field are all now deceased. In the 50s, Stammel and Veronis began collaborating at the IAS, within the von Neumann and Charney project, but their ultimate approach was to understand detailed processes rather than to study forecasting.
A GFD school began in 1959, with the aim of introducing a third, relatively new topic in mathematical physics, geophysical fluid dynamics, to graduate students in physics sciences. It has been held each summer since and promotes an exchange of ideas among the many distinct fields that share a common interest in the nonlinear dynamics of rotating, stratified fluids. These fields include classical fluid dynamics, physical oceanography, meteorology, astrophysics, planetary atmospheres, geological fluid dynamics, hydromagnetics, and applied mathematics. https://gfd.woi.edu. 115. It is worth emphasizing that before the availability of computing, progress in explaining observations or making predictions in all of the physical sciences, including climate science, was made using pencil and paper calculations. Computers changed this completely and inter era precisely, during which both theory and numeric modeling in this field were developing. For this reason, a conceptual bifurcation occurred, in which numeric realism and simple theory began to evolve separately, and the generality of the latter was largely viewed as handicap rather than a great benefit, whereas numerical climate models are only specifically relevant to the system under study. 115. After roughly half a century, the theory of climate is now demonstrating its realism as well as having touched many fields in dynamical systems along the way. This is due to the fact that nonlinear systems create emergent phenomena, whereas GCMs act as a variety of ways as filters of high-frequency processes.